So, actually, based on calculations, right, you can predict how fast Usain Bolt run, is it? Can I say that?
With enough data, it's possible. We can calculate his muscle, skeletal,
Yes.
output force.
His height.
Yes, aerodynamics.
So hello and welcome to SembangTech. I'm your host today, Judy, from the marketing team at IP ServerOne. Now, normally in our SembangTech episode, we speak to IT industry people and the peers. But today we got to learn and hear from student instead, a student from Monash. So welcome, King Wei.
Thank you.
Can I call you King Wei?
Yeah, sure, absolutely,
Okay.
please.
So welcome to our humble abode in IP ServerOne.
Oh,
So we're at our office actually, a small meeting rooms here. So welcome.
Thank you.
Okay, first of all, I think let's try to understand a bit about King Wei. Who is King Wei?
So I am actually a final year engineering student from Monash University. My specialization is in mechanical as well as fluid dynamics, and my projects mainly focus in that aspect as well.
Okay, so when we talk about mechanical engineering, why did you get into the role in the field?
A lot of people ask me that question, right? So for me, I'm a very hands-on kind of person, right? I really like things that are mechanical or calculative, right? So that's why I joined mechanical engineering, because it's a very mathematically intense course.
Mathematically intense
Yes.
course. So I'm thinking you gotta calculate what physically how the speed move and whatnot.
Absolutely, yeah, everything actually, even how this entire building holds up, why is it structurally sound, or even the HVAC ducting, or the air we breathe in, the rate that we breathe in the air, right? That's all calculatable. We think things in terms of mathematics, so we try to derive them mathematically.
So can I confirm is using AdMaths?
Yes.
Okay, so for students that in your Form 5, you study AdMaths, if you want to learn mechanical engineering, you better learn your AdMaths.
You still can make it. You still can make it as long as you put in the hard work. You cannot make it as long as you wish for.
Okay, so let's say once you, because you're final year, right? So once you graduated, where you'll be working actually?
A lot of different areas. If we are talking in terms of fluid dynamics, right? Jobs that specifically require our specialized knowledge in terms of design, for example, like car aerodynamics or HVAC or R&D, right? That's where we'll come to be useful.
Now, can you tell us for people non-tech like me, what is CFD in layman terms?
Okay, so to understand CFD, before that we have to understand what's fluid dynamics. So in the 1800s, right, we have these two persons that are very genius, one Irish, one French, Louis Stokes, and another one Louis Navier, and then Gabriel Stokes. Both of them came up with this brilliant equation called the Navier-Stokes equation. So people realized that we can take this equation to model anything that flows, air, liquid, or anything fluid in general, right? So we can predict the movement, the behavior of flow, but then to calculate it, right, by tradition, people use hand calculations. So they discretize the equation into a finite grid, maybe a volume, 3 by 3 space.
Okay.
But then to do that, right, every single equation, you need to do it once. It's very repetitive, it's very intensive, right? And one problem can take hours, days, weeks, or even months just to solve one problem. So after the invention of computers, people realized that you can instruct computers to do repetitive tasks, right? So people basically inputted these instructions in computers to solve these problems. And nowadays, our technology is modernized so much, right, that we can basically model something, throw it into a CFD package, and then they'll model the flow behavior for us in just seconds. And that's what we call computational fluid dynamics.
I see. Okay, to me, stupid technical, no. Okay, maybe we can use an analogy. For example, okay, so I understand in CFD, you're actually trying to do some calculations.
Yes.
You don't need to build a physical prototype to understand or flow,
No.
see how the things flow, right? Now, if we put it in a simple term like aeroplane, can we use analogy like?
Absolutely. So aeroplanes, they fly through the sky, right? But why they fly was because there's a generation of lift force for the plane, right? And to model that lift coefficient as well as drag coefficient, we can use computational fluid dynamics to mimic how the plane will fly in actuality.
Okay, so you have a plane.
Yes.
You gotta know what size of your plane is.
Yes.
Correct?
Yes, correct.
So then from the size of it, you can roughly calculate the airflow, if rain heavy, thunderstorm,
Yes.
turbulence.
Yes. Density of air, if you're going up hundreds, thousands of feet, you can simulate that.
Okay, once you have all these calculations, basically you use this calculation to build the aeroplane, right?
Yes, correct.
Oh, okay. So it's like if I want to build rocket, I must know lah, like how fast I can just...
Actually, yeah, you guys have heard of the very 1960s stories about the Apollo rockets going to the skies, right?
Yes.
Back then they have like 8 megabytes of RAM or 16 megabytes, correct me if I'm wrong, but basically they use these megabytes of RAMs to calculate how the rocket would behave in thin atmosphere. So that's why they consume so much computational power back then. That's the earliest form of computational fluid dynamics actually.
Okay, so talking about technology, right? Aside from using cloud computing to calculate your CFD, is there any other technology that you can actually use?
So, well, cloud computing, right? Conventionally, we use CPUs to calculate, right? But in terms of hardware, people have figured out that you can use graphics cards because graphic cards, they process things in matrices, right? And CPUs, by tradition, before AVX 512 came by, things were processed in sequentially. So people have been trying to get on, scientists and engineers, they're trying to invent a way to develop this much more mature CFD package natively on GPUs that can accelerate way faster than CPU solvers.
Of course. And also in CFD, actually, if you break up the model size to smaller pieces, the calculations will be more accurate.
Yes, correct. So in the software, we call that step called meshing. So you have, before you solve for the fluid dynamics, right, you want to ensure the domain of the flow as well as the model itself, it's fine enough and accurate enough to produce a reasonable answer, right? That's what we call, quote unquote, as cutting down the model, right? And yes, as more accurate as you get, the costlier it gets. Yes, correct.
And then, of course, using cloud, you have all the CPU. The smaller your model, you're going to use a lot of CPU, storage size and everything lah.
Yes, correct.
Understand. Okay, so what about physical server or bare metal?
Bare metal, yes, we've traditionally has been using bare metals for our workload, right? But the difficulty of bare metal is that, one, it's not scalable. If you have a project that suddenly bulged in size or exploded in size, right, you can't adapt to it. With cloud computing, right, we can. That's the biggest advantage. As big as you want, as small as you want, you pay as you use. Yes, that's the biggest advantage.
I see. Now, talk about cloud for CFD. So you said earlier it's important to have the scalability. It's important that, as a student, you want to save costs, right? So if you're doing the model, then you pay for more. If you're not, then you scale it down, right?
Right.
So aside from the scalability or performance issue, do you see any concerns or limitation using cloud for your CFD?
With cloud, right, the traditional concerns has always been security. Security has been a big focal point. But with IP ServerOne, right, they came out with a lot of very great security features that made me very comfortable with running my projects on the cloud. Even not just for me, right, for other project managers or even, say for example, F1, right? You know their cars, why their car look like that? Because of aerodynamics. And then how they achieve that simulation data through cloud computing as well. So with such fierce competition, not just in F1 or like your company tendering for a project or you're coming out with a new patent, right? Security is crucial, it's imperative. So I find IP ServerOne to offer very good security in terms of that.
Okay, so you talk about the importance of security for your data. Can I just ask a bit deeper? Is it you scared people steal your data, or is it after you do all the calculation later, ransomware lost already?
All of that, actually. One is that if you are in a highly competitive environment, right, it's very possible that people try to sabotage you, try to get your data. But I am not fortunate for that. But
not
other
for
than
not now.
Not now. Security, not just in terms of people sabotaging my data, right, but also in terms of data loss. Yes, because with conventional bare metal, right, or our own private desktops, right, it's very probable that our hard drives get corrupted after so many writes and reads, right?
Yes.
The I/O performance drops and
Yes.
you lose all your data. With IP ServerOne, we have redundancy. So that's one of the key features that I look for in a cloud computing partner. It offers me comfort in my sleep, knowing that I won't lose my data out of the blue.
Yes, so for NovaCloud, basically it comes with not just security groups that you can actually tweak your server. You don't want anybody access it, or
Yes.
you only allow certain ports that is open. We also have built-in like automated snapshots backup.
Yes.
We don't charge you for it, so in case like data loss or there's just corruption happen, you can just reverse to the real point of time.
Yes.
Okay, so how do you manage the cost? I mean, because you use so much of
Yes.
the CPU and the storage.
Yes, correct. Good question. So with conventional cloud computing, right, scalability becomes a problem when your software is proprietary. But fortunately, my entire software stack is all open source. So I run Ubuntu, OpenSUSE, then my CADing is on FreeCAD, which is an open source CAD software. On top of that, to mesh, we use Salome or Gmesh. Then after that, finally, we use a software called OpenFOAM. All these packages are open source. So one, they are free. And then two, they're customizable,
Yes.
tailored to your needs, as long as you know how to code.
Correct.
But with the onset of Gen AI, right, we find it very easy to adapt these software to what we need, including to scale. So in order to scale, right, proprietary software, you have to go through their interface and then get in with their partner. Then only when you can scale your calculations. But with open source, no. You can just DIY
Correct.
everything.
Correct.
And that's why I find so convenient and so helpful when trying to reduce my costs as a student.
I think not just that, a lot of customers or businesses in Malaysia, a lot of us is actually quite cost conscious.
Yes.
So we would rely heavily on open source. A proprietary, yes, you are enterprise, you have a lot of budget to spend, but I think ultimately open source is a good choice.
Right.
Yeah. Okay. But then you using open source, how then you make sure your data security then?
That's where the security, the packaging of the cloud computing comes in. Because our cloud computing modules, right, clusters, right, are one single cluster, right? So we make sure we don't interact with anything outside other than our work scope. Once we are done with it, then we transfer our data to another server. Then we eliminate that cluster.
Okay. But then with the rising, now we have AI, right? Can I ask you a straightforward question?
Sure.
Do you think engineers still need for CFD if I can use AI to calculate?
Absolutely, yes. There is a must for CFD perpetually, as long as you have something that's moving in fluid, in atmosphere. AI, yes, they can assist in our calculations. In the industry, we have something called physics-informed neural network. It's a different type of AI that you guys have been using every single day to write your codes or to chat with.
Okay.
So it's more fundamentally a machine learning model that learns the patterns of your equations.
Okay.
Going back to a Navier-Stokes equation is a PDE equation,
Okay.
right? So it tries to solve that equation or predict it rather than trying to solve it, discretize it into a finite grid. And that, rather than trying to sabotage our careers, right, I've been seeing a lot of great advancement in the industry because of these advancements in technology. So I think in a general sense, AI is not to fear, but rather to embrace it and to leverage it to further our inventions and innovations.
That's the correct mindset. Okay. Now, how actually you come through IP ServerOne? Where do you heard it from us?
I think a lot of people would think of the billboards, right?
Yes.
Your market budget,
IP ServerOne.
yes, IP ServerOne. Well, the marketing budget has been great, absolutely phenomenal. But I first came across IP ServerOne when I was cross-shopping for cloud computing partners, actually.
Oh,
Yes.
So you mean you're researching?
Yes, there are a lot of providers in Malaysia, but none that can exactly meet my specifications. So that's why I came to IP ServerOne, because you guys offer great features, great support, as well as great cost. That's the most important thing.
Okay, so let us just understand a bit now. Technically, right, how do you actually use it?
I deploy all my software onto a new instance. Then I throw in my model, my already meshed up model, into the module. I run it, I get the data, then I get the data out onto another server for analyzing.
Another server means you spin up another NovaCloud instance and just dump all the...
Could be or could not be, depends on the instance or the scenario, if there's a need for it.
I mean, why you do these steps? Like, why are you taking out the data, not just proceed with the same?
Because I have a lot of clusters running simultaneously. It's hard to combine everything into one server, then you suddenly forget about it, then it gets very messy. So I usually allocate one last cluster as the final one, because the one last cluster, right, I run a lot of analytical programs on it as well. So Paraview, if you guys are in the industry, as well as Python, and then MATLAB, right? MATLAB is proprietary. So regardless, I have to go back to that one single machine for analyzing.
Oh, so you just do put everything inside and then analyze the last one.
Yes, correct.
Understand. Okay. So how easy is it actually to use NovaCloud?
Very good, actually, I find. Because my projects, right, sometimes you're bloated in size unexpectedly. Sometimes you require computational work more intensively, or they need more storage, right? With NovaCloud, I can scale very effortlessly. I have the option, do I want more storage or less storage? Do I want more CPUs or less CPUs? If I need less, I just cut down my costs. Only pay as I use. So I find it very, very convincing, very cost effective in terms of that. But also the support as well has been impeccable. So IP ServerOne, they have all the documentation laid out already. And if you still have problems, right, you can reach out to their 24 hours support for that. And they are very technical people.
Thank you for doing the marketing for us, King Wei. I guess I don't have to say much. So normally to do your CFD project, right, like when you are modeling the size or you're calculating the flows, roughly how much data transfer usage you'll be using, or maybe CPU that you'll be using at one point?
Oh, it really depends actually. Small projects, you can take like just one single core, maybe like 500 megabytes of size. But yesterday I just had a project, right? I was running it on 32 cores, and then the storage took up about 1 point something terabytes.
Oh, that's big.
Yes, a lot of numbers.
Oh,
so it really depends. It's really hard to say. But for bigger projects, I believe there's a need for bigger storage. Unfortunately, IP ServerOne, I believe you guys offer up to 1 terabytes of free data transfer, right?
Every month.
So that can come in very handy when you're facing these kind of situations.
Oh, okay. So when you no longer need it, 32 core, you just scale it down now. It's not like it's there for a few months,
Absolutely.
Right?
It's very cost effective.
Okay. Now, I want you to draw something for me. Again, so we spoke about CFD, we spoke about how it used on aeroplane, how it calculates. Now you give us some visualize, right? For example, you draw an aeroplane. So what is it you're calculating?
Okay.
Is it doable?
It's doable, but everybody has been thinking computational fluid dynamics as like this wizard kind of a thing, a magical kind of thing, but it's not. It's basically just imagining how the little particles of air that moves around us, we are calculating how they move around us. So for example, you have like a plane, right? Imagine it's like a plane. It doesn't look like a plane, but looks like a plane.
Now, for easier for everyone to learn, and also myself, right? Come, let's draw an aeroplane.
I am a horrible artist.
Engineers
can't draw.
I think my editor can draw out an aeroplane for you.
Sure, absolutely. So aeroplanes, we have a head here, right?
Correct.
And then it's like a tube shape, tiny tail, winglet. We have wings here also. And then we have the big wing here.
Correct.
So with aeroplanes, they fly in space, fly in air, right? So we have airflow here, airflow here. And aeroplanes that wings, right, are usually tilted to gain.
You mean they are not fly like that? You mean the wing is not like that, it's like that?
More exactly, the wing, what we call this shape is an aerofoil shape.
Oh,
yes.
You mean the shape of the wings?
Yes,
yes, it is.
It's an aerofoil shape, right? So as air passes through, airflow passes through, right?
Yes.
With computational fluid dynamics, what we are imagining is that these little particles of air, how are they flowing through the aerofoil, or rather the shape itself? And then as long as they fly through air, right, there's a force that's generated called the lift force.
From down there.
Yes, it pushes the plane up. That's why aeroplanes can fly. And then after they fly, right, they'll generate a what we call a downstream wake. This is the wake. So with computational fluid dynamics, we are imagining, or rather visualizing, this entire domain, how it looks like, what's it like, why does it happen, and then as well the mathematics behind it.
Now, where does gravity comes here?
Gravity always points down, but the lift coefficient must be greater than the gravity for the plane to fly up.
So how you get the lift?
So you know plane tips, right? They are angled sometimes.
Yes.
When you have wind pushing through, right, you generate an area of lower pressure here and higher pressure here. So the high pressure pushes the plane up, and then the lower pressure keeps it up, like that. So this is low.
And that is high.
This is high.
So therefore it can lift.
Yes. It generates a lift force via that way to overcome the gravity. That's why they can fly.
I see.
Yes.
Then how about why is the head? The tail of the plane, it looks like that.
Pointy.
Oh, so this one, it doesn't matter. They just do it for like
It
style.
does matter. No, it's not just for style. Everything has a purpose in engineering. So why planes, their tails are pointy, right? When you imagine flow, let's take this back, for example, right? Air passes through.
Yes.
They split up at the head, which is round.
Correct.
But then at the very end, right, they need to recombine back.
They need to come back.
Yes, the boundary layer, what we call boundary layer, they need to reattach
Okay.
in order to minimize drag. If, say, we are flying through a flat shape end, right, the flow goes like this. Yes, but then there will be reattachment.
So what will happen if the plane is like that?
You can't fly.
Oh.
There's too much drag. You can't get enough speed.
Oh.
Then you don't have enough lift. Then you fall down. That's why planes, or not just even planes, birds, their tails are like that also. Even Mother Nature has thought of everything. Evolution is according to optimization. They have already done the CFD on themselves. Yes.
So this one is just we're taking from the nature and then we apply in our daily lives.
Yes. A lot of things in engineering are actually inspired by nature. Mother Nature is the best optimizer.
So actually, based on calculations, right, you can predict how fast Usain Bolt run, is it? Can I say that?
With enough data, it's possible. We can calculate his muscle, skeletal,
Yes.
Output force.
His height.
Yes, aerodynamics. Maybe probable, but we are not at that stage yet.
Okay.
Maybe in 100 years or so.
Okay. Well, who says with AI you can actually fasten the process?
Maybe on a GPU platform, yes.
Oh, if like that, then in future when the students want to go into some athletic school, say, so they have to go through this certain skill set calculation check first.
Actually, yes. If you go into modern athletic schools, right, you see athletes, right, they put on their mask and then they run for very fast, right?
Yes.
What they are doing is that they are basically taking data and calculating the force output versus their, for example, like weight or aerodynamics or whatever, right, to optimize for their results. Even biking, right, cycling, right, you see cyclists, they have their
The helmet pointy behind.
pointy, and then
Yes.
they are all leaned down like
Correct,
that.
correct.
And then the bikes, it's one flat disc, right?
Yes.
It's all for a purpose. They're engineered in a lab.
So the tire is skinny for reasons.
Yes.
Okay. Wow. Okay, I
Yes,
learned a lot of
yes.
things. Okay. Can you just tell me, like you have using NovaCloud for a few months now, right?
Yes.
Is there 3 things you can tell me that you like about NovaCloud?
It goes back to what I said just now, scalability. My favorite thing. You don't pay for what you don't use. Reduces wastage, reduces energy usage, sustainable goals. That's very important to me. Secondly is security as well. And then also the support features. The 24-hour tech support has really saved my ass a few times, to put it bluntly.
Okay. All right. Now, we just want to ask a bit more high-level questions now. Like we dial it up or dial it down a bit. How do you see CFD contributing for future innovations, or in your field specifically, or maybe beyond?
Okay, so with computational fluid dynamics, right, it's been around here for a few decades already, but I believe it will stay here for the end of engineering, really. Because anything that needs to be engineered, right, will always require the use of CFDs. And then in terms of innovations, right, with AI accelerated workflow, right, we can calculate for much more complex structures as well as projects. So bigger airplanes, bigger HVAC ducting, bigger P&ID, like chemical plants flows, bigger projects in general. That's where the main innovation comes into play.
So what about, certain countries, they are very susceptible to like typhoon or tsunami or, earthquake.
Absolutely.
Does it come in?
Absolutely. So a lot of weather prediction, right, in terms of rain precipitation or like cloud formation, right, they're all calculated on supercomputers actually. So all the predictions made, right, are made inside a data center running the same software that we are running actually, just on a way larger and larger scale. So in terms of innovation, yes, with greater efficiency as well as computational power, right, we can predict further, predict more accurately, and predict better. Not just in terms of weather, but in terms of a lot of things. F1 also. Every year they came out with a new aero package. That's all the money went into R&D.
Looking ahead, right, how could cloud provider like IP ServerOne can actually help you to focus more on your innovations?
For me to focus on my innovations personally, I think to provide a good quality product, that's what attracts returning customers. You can price it very cheap. You can price it whatever you like. You can attract customers, but those customers, they don't really care about the core product itself. They only care about the price, which a lot of people do. I do care about. But you're providing a good product at a reasonable price. That's what a lot of consumers, they make the cost to performance reports on that, right? That's what they care most about, honestly. People want a quality product at a reasonable price. That's how IP ServerOne can further grow their market share.
Okay. Now, aside from the costing wise, right, are there anything potentially you see NovaCloud can actually improve on?
Absolutely. I think one big thing is making its impression on especially students like us. Because we are the future decision makers, we are the future project managers.
Yes.
We decide what products to be bought. The next generation, the next decade comes around in newer companies, right? The most important thing is to make the impressions on us. Let us know your presence, let us be familiar with your platform. A lot of marketing strategies, even the Milo you drink.
Yes.
Right. You remember the school trucks that came into your primary school, right?
Yes.
That's your marketing strategy.
Correct.
A lot of firms, tech firms, they aim for this strategy nowadays. Honestly, it's a very good strategy, provided that you know you can stay around for it. Then you stay around for a few decades, then your ROI comes back.
Correct.
Yes.
So they start feeding you Milo since you are young until
feeding
you are
me servers cloud
I feed you
infrastructure.
servers lah.
Yeah, my GPUs
feed
me GPUs so I can run my AIs on.
Can. I see. Okay, so are there anything else that you would like to share with us?
I just want to say a huge thank you for IP ServerOne for supporting my project. It's been my greatest pleasure to work with you guys. IP ServerOne, I guess.
So thank you, King Wei, for being here today. So I look forward to your finalized project. It hasn't been out yet, right?
No, absolutely not. We are still working on it.
So roughly when can we see?
It's hard to say. Publishing a paper takes a long time, People take, some people take decades to write a paper, and even their finance the paper. It takes years to get them reviewed and edited. But we'll see. We'll see. Maybe in the future, maybe next year. We don't know.
You will. Thank you so much for tuning in to SembangTech by IP ServerOne. If you want to hear more stories about cloud, AI, or the people behind the technologies, stay tuned for more. Until next time, ciao!